Hi students, this is Ms. Fisher and I am so glad that I can be here today with you to explore geometric probability. So, before we get started, make sure you have the note sheet that says section 13.3 on it, geometric probability. Yours is going to look a little bit different than what is on the video right now. That's okay. We'll get there in a second. You're not actually going to write anything down yet, but I just want you to be ready. I will follow along the note sheet after I give you a quick introduction. So our objective today is to calculate geometric probabilities and use geometric probability to predict results in real-world situations. My first question to you is, I know you've heard the term probability before. What do we mean when we say geometric probability? Because I doubt that you've ever heard the word geometry or geometric put with the term probability before. You've probably seen probability that looks something like this, where we have a spinner, one example, or a dice, something like that, and we're asked what's the probability of rolling a 1, or what's the probability if you have 4 equal sections as shown on the board, what's the probability that the spinner will land on the yellow section. I know it looks orange up here. We're going with this one as the yellow section. It's just a little bit off, and hopefully my board's going to let me write on it. Oh, there we go. It's just doing its antics. See, it's just like if I'm here. Now you can picture me hitting the smartboard, right? That's what's happening right now. And I'm going to erase that and try again. There we go. Yeah, there's definitely a delay. So we've got the yellow section there, and the question is, what's the probability of rolling yellow? So I'm going to spin my spinner, and it may or may not land on it. And supposedly, if there are 4 sections, we would think that the probability of it landing on the yellow section would be 1 in 4. And there we go. That was the 4th one. And how about that? It landed on yellow. Now, what if I ask you what's the probability of it landing not on a section that's not green? Not all at once. You're right. 3/4 because there are 3 sections that aren't green. And the last one, red or purple or blue, whatever you want to call that, last 2 sections there. Since there are 2 of them, they're equal sizes, we're going to say 2 out of 4, and let's go ahead and make the habit right now that we are going to reduce all of our fractions, because our probability answers will be fractions. We're going to put our answers in reduced form, just like we've been doing. And for the most part, that is probably what you have thought of or seen in terms of probability. That's probability. You've got it. Now, why do I say geometric probability? It's not just because we're in geometry class. The probability that we're going to look at today is going to be different. Let me give you an example. How does this spinner compare to the spinner we were just looking at? Okay, I know there's 5 sections instead of 4. I can count. But what's significantly different other than the fact that there's 5 sections? If you were thinking something along the lines of the fact that they're different sizes, you are exactly on track. So I want you to go ahead and flip your paper over. We're going to come back and define geometric probability in a second. Let's go ahead and do this example because I want you to ponder. I'm on example 4 on the back side. It's not the first one on the back. It's the next one down. Find example 4. I want you to ponder what would be the probability in this case of the spinner landing on the yellow section. Would you say 1 out of 5? There's 5 sections, just like there were 4 sections last time. 1 of them is yellow. How many of you say 1 out of 5? Good. I'm glad none of you raised your hand because we just said that the sections are not equal. So common sense is saying, well, no, it's not equally likely that I'm going to hit this little purple section over here as it is I'm going to hit the yellow section because clearly the yellow is bigger. So what am I going to do to account for the differences? If you have an idea, jot it down. I'm guessing a lot of you figured it out without even knowing what geometric probability is, and you just used geometry to compare the sizes of the regions. Now the problem is when we talk about probability, we have a real simple definition for probability. Probability in general, not geometric, I'm just talking probability right now, is a fraction, and we like to say something like It's the event. How many ways is there of something happening? This event changes depending on what I'm talking about. Over what's the total number of possible outcomes in a situation. Now, the problem is that in this situation, here I could count and say that there were 4 outcomes and all were equally likely to happen. There's my 4 in the denominator of all 3 of my probability fractions. When I get to here, I have 5 sections, but my denominator is no longer 5. Instead, I have to consider each and every case of where my spinner could land. So my spinner could land right here. My spinner could land here. How many different places are there where my spinner could actually land? Now, that's a hard question to ask. In fact, I'm going to say so hard that it's actually impossible for us to answer. So good news is that geometry, once again, is coming to the rescue to help me figure out probability when I don't know the total number of outcomes. And in fact, there is no way to figure it out because we have an uncountable number of outcomes. Okay, an infinite number of outcomes. That's the first part of geometric probability. The second part is how do I calculate it? And I'm going to use geometric measures. So going, back to my spinner. If you wrote something on your paper, I said if you had an idea, jot it down. If for letter A, probability of the spinner landing on yellow, you put 120 out of 360, bingo, you're right. Why? Because 120 degrees is the degree measure of that sector of my circle, and I know that the whole circle has 360 degrees. So you're comparing the measurements, you're comparing the sizes by using the degree measures. You just use geometry to calculate the probability of a situation where we have an infinite number of outcomes. Go ahead and try B, C, and D. So go ahead and just do some quick calculations. Good practice with our fractions. I know you love the fractions. If you want to pause the video, and then check your answers. Okay, hopefully you had a chance to try those. I know you're probably wondering where the orange section is. Okay, that reddish looking section, it looks orange on my computer, red on the board, that's just how it works, is my orange section. So I'm going to get 90 out of 360, and you should have had 1/4 for a reduced fraction there. Yellow or orange, I'm doing 120 plus 90. So 120 for my yellow plus 90 out of my total 360. That's giving me 210 over 360, which comes out to be reduced form 7/12. And neither yellow or orange, 2 ways to do this one, I like this question. Neither yellow or orange, one way you could have done it is add the other 3 sections, 60 plus 45 plus the purple section, 45. Put that over 360. And that would have given you altogether, what we have, 150 over 360, reducing to 5/12. There's one other way to get that answer. Look at the relationship between letter C and your answers to letter C and D. Does anybody know the name for D when we're comparing it to C? We call those complements, complement events, because together they cover all the possible outcomes that could happen. So C says, what's the probability of yellow or orange? And then D says, neither yellow or orange. Well, if it's not yellow or orange, C, then it falls in the D category. And therefore, together, those 2 probabilities of complements always add up to 1. So the other way that you could have gone this, kind of a shortcut, would have been to say that my probability for D has to be 1 minus my probability for C, which was 7/12. And that would have also gotten you 5/12 if you did a little quick conversion here, that 1 is really 12 out of 12. 12 minus 7 giving me the 5 over 12. Okay? So, a little bit of review of some other maybe probability things that you've heard before. And a good introduction to geometric probability. Let's flip your page over. back to the front side. Join me, we're going to define geometric probability. Okay, you saw an example, I kind of verbally said it, let's write it down. Geometric probability is probability, actually, we need to write that. Let's just say involves an uncountable or infinite number of outcomes. So it is figured based on a ratio of geometric measures such as segment length, areas, arc length or arc measures, and I'm going to put etc. because we could have others. Those are the most common ones. We already saw the arc measures. Now we're going to go ahead and look at how we could use segment lengths to calculate geometric probability. And here's where the real world stuff comes into play. We've got a series of commuter shuttles stopping at a given station every 20 minutes. This happens in just about every city in the world, I would guess. The length of time each train, apparently our commuter shuttle just changed to a train. So it's a commuter shuttle train for the rest of this problem. The train stands at rest at the station for 4 minutes. If you arrive at a random time, what is the probability you will be able to board the train as soon as you arrive at the station? Okay, we all like to get on as soon as we get there, right? We don't want to have to wait. So what's the probability that you are going to be able to actually get on the train as soon as you arrive? So my first question to you would be probability. Event over total. Well, what's the total number of possible times at which I could arrive at the train station? How many different times if you were to count them? And if you're thinking minutes, not good enough. We have 20 minutes, but there are certainly times within that minute, that any one of those minutes that I could arrive. If you're thinking seconds, still not good enough because there are times within the seconds that I could arrive. And hopefully you're agreeing with me that we have an infinite number of possible times at which we could arrive at the station within my cycle of 20 minutes when the train is coming in and leaving. So I'm going to suggest, we're in geometry class, let's draw a picture of what's going on. So here's my picture of my train shuttle cycle of 20 minutes. So this whole line represents 20 minutes. By the way, just quick review from chapter 1 in geometry. How many points would be on the line that I've drawn on the board? Hopefully you said infinite. If you said 2, wrong. Infinite number of points, so I've got infinite number of points there. Length of time each train stands at the station is 4 minutes. So I'm going to put 4 minutes right here. And actually, I'm going to do that one red because that's like kind of like my stop time, right? 4 minutes it stopped, and then it is gone for, whoops, not 20. What would be the green segment? If the whole thing is 20, well, there's no train there. The train's standing there for 4 minutes. There's no train for 16 minutes. So it stops every 20 minutes. Every 20 minutes. Then we repeat. So now we've got a train here for 4 minutes, and then we've got 16 minutes where there's no train. And then we've got a train that comes and is here for 4 minutes, and then 16 minutes where there is no train. And if this cycle keeps repeating, and I'm worried about probability, I'm going to keep it simple, and I really only need to look at one of those cycles. So what's the probability I will be able to board the train as soon as I arrive at the station? Well, if I get there right here, can I get on the train? Sure. The train is sitting right there. It's sitting there for 4 minutes. I'm going to have to sit there for 4 minutes until it leaves. If I get there right here, can I board the train? Yes. If I get here right here, can I board the train? As long as it hasn't left yet, but as soon as it leaves, which it's just about to leave, there is no train there. So if I get there right here, can I board the train? No, there is no train there. So I can only board the train if I get there within the 4 out of 20 minutes of the cycle of this particular schedule of commuter train. Reduces to 1/5 would be my probability for that one. Okay? Using segment length to calculate probability, where I can't count the number of outcomes. I can compare the lengths of the segments representing my cycle here. Part B, and 20 times of going to the same bus station. Okay, so it's now back to a bus, not a train, but it's the same thing. How many times could you expect to board the train as soon as you arrive? 20 times. I have my probability. Quick little review. If you're not used to this, I can take my probability and I multiply by the number of times that I'm going. And that's going to give me the number of times that I should expect to be able to get on right away. So answer there is going to be 4 times. The other way to think of that is you could say 1 out of 5, if you like proportions, you could set that up as a proportion. 1 out of 5 equals x out of 20. If you can board it 1 and 5 times, how many times and 20 times could you board it? So supposing I use the same process, if I arrive 60 times, how many times can I expect? Well, I'm going to take my 1 out of 5, and this time I'm going to multiply times 60, giving me an answer of 12 times. Every day for an entire year, because you work somewhere where you have to take this commuter train to get to your job, and you're just wondering how much time do you waste standing at the station and how many times you actually get on right as soon as you get there. Because you would probably wonder about these kind of things if you're riding on this train. So I'm going to multiply by 365 this time. Hopefully you're catching on to this idea. And that'd be about 73 times. Okay. Hopefully you followed so far, because I'm just about to blow your mind. At least I warned you. Letter C. If you arrive at the station and there is no train waiting, what is the probability that your wait will not exceed 10 minutes? I told you I was going to blow your mind, right? Let's interpret it part by part. If you arrive at the station and there is no train waiting. No train waiting. So let's go back to my scenario here. Which part represented the train not being there? Kevin, yeah, you're right. It's 16, the 16 part. The green right here was the no train waiting. What's the probability that your wait will not exceed 10 minutes? Okay, so let's go back right here. And if I came right here and the train had just left, how long am I waiting until a train gets there? Yeah, Michael, you got it. If we remember, there was really a train that came right here at the end. So if I get there right here, I'm waiting 16 minutes. Is that exceeding 10? Yes, 16 is more than 10. So I want to know what's the probability my wait will not exceed 10 minutes. Well, it's going to be more than 10 minutes until I get 10 minutes from the end of my segment right here. So for these 10 minutes, these last 10 minutes, I should use a different color here, I'm waiting 10 minutes or less, not more than 10 minutes, out of total, be careful here. My total here becomes the 16, not the 20, because I'm told that there is no train waiting. I didn't mean to cross that out, I meant to highlight it. There is no train waiting, so I know that I'm not including the 4. So correct answer there is going to be 3 out of 5. Not 3 out of 5. I can't read these fractions. Let's try 5 out of 8. That better? Okay, you're going to try D and E. Go ahead and try them. Pause the video. and then check back in. That way I don't have to make a 48-minute video. You guys can try it and then turn it back on. Okay, you pause the video, you tried them, and you should have gotten for D. What's the probability you'll have to wait more than 5 minutes? 11 out of 20. Let's take a look. I didn't tell you that there is or isn't a train waiting, so we're still considering the whole interval of 20. Wait more than 5 minutes would be, if you're looking at the picture, this was 10 minutes or less. So I'm going to go 5 minutes from the end here. More than 5 minutes would be all of this. I'm waiting 6 minutes, 7 minutes, 8 minutes, 9 minutes, 10 minutes, 11 minutes, 12 minutes, 13 minutes, 14 minutes, 15 minutes, 16 minutes, depending on where I fall in that interval. So that's actually 11 units long compared to this 5 for the 16 total. So that's where I'm getting the 11 from, 20 for the entire denominator. Given that you have to wait, what's the probability you have to wait more than 5 minutes? And the only thing you're changing here, hopefully you picked up on this, given that you have to wait, same thing as I had a change in my denominator there, given that you have to wait, should have changed it to 11 out of 16. The 11's the same as in D, but this time my denominator is 16. I'm only considering the green section where I have to wait, not the whole section. Good news, that was the hardest one that we're going to do. You're going to try example 2 right now, which involves a stoplight. So picture you're leaving Mentor High School. You're at that famous stoplight, trying to turn left, which I try to do every day after school. And you have to agree with me that that is the longest light in all of Mentor, I would say in all of Ohio. And you have to wait there far longer than the light is actually green. So I'm going to say that there's about a 99% probability that I'm going to have to wait when I go up to that light. But what if we actually tried to calculate it? What if we measured how long it was green, how long it was yellow, how long it was red? What's the probability that we would have to wait? So I've given you an example with a stoplight in example 2. Clearly not that stoplight because it actually is green for a whole 25 seconds, and that stoplight is green for maybe 5 seconds. Go ahead and try and get A, B, and C. Pause the video. Yes, that means physically somebody get up and go to the smartboard and actually pause it. Those are the parallel bars that look like this. Yes, pause it and waiting. Okay, I'm glad we hadn't figured out how to pause the video. I'm back with you. Let's check and see how we did. Quick little visual of what we got. I had a picture that looked like this. 25 green, 5 yellow, and 30 seconds of red. There's my stoplight, and then it starts all over again. This is just kind of a timeline here that I'm showing. What's the probability when you arrive that it will be yellow? And we should have gotten 5 out of 60, giving me 1/12. How many of you got that right? Excellent. See, I told you you could do this. Okay. Part B, what's the probability you have to stop and wait more than 10 seconds? And now you just said, oh dear. More than 10 seconds. So we're waiting in the red section, right? That's what red means, wait. So more than 10 seconds, you should have identified that this 20 seconds of my 30 seconds of wait time, I'm waiting more than 10 seconds. So I got 20 out of 60. Notice that I did not change my denominator to 30 because I didn't know that I was waiting. I'm still considering the whole interval. And if you arrive at the light 50 times, how many times should you be prepared to wait? More than 10 seconds. We're taking our answer from B and multiplying times 50. Not a whole number, about 17 was my answer. How'd you do? Okay? Okay, flip the page over. Practice sort of just some strict geometry. I'm not putting a problem situation with this, although we could. Let's see what we get. The scenario is, we know that the length of AB is equal to BE is equal to EF. I'm going to mark that as best as I can. AB is equal to BE is equal to EF. We also know BC, CD, and DE are equal. So those are these little blue guys are all equal to each other. What's the probability that a point selected at random is between B and C? And I'm not told any lengths here. I'm just told relationships between B and C. Take a guess. You have a guess? Could we maybe represent these with something? I have a couple ideas. We could put some numbers there. We could put some letters. Would probably be the best so that we're not assuming anything. Could I call each one of these blue sections X since I know they're equal? If I call one X, then they're all X. Okay, so then this red section from B to E is 3X, and I happen to know that that's equal to AB. Now this is 3X, and EF is also 3X. Now I can compare lengths because they're all in terms of X. Between B and C would be 1X out of how many total X's for probability. I need the whole length, and what's the probability that it is between B and C? I'm going to assume that it could be any point on the line. I'm getting 9X. Simplify. You're right, the X's cancel and we get 1 over 9. You might have gotten that just by looking at it and then just kind of putting some numbers with it. Maybe you just said this was 1 and each one of those is 1. Between C and F, this is where my variables are going to be helpful because now I'm actually going to look at this length here between C and F, and I'm going to have to say that I've got 2 X's plus 3 more X's, so I'm getting 5 X's for my numerator over denominator still 9X, cancel the X's, 5 over 9. Okay, those are some examples of using segment length, what we did on the front side, and what we're doing right here to calculate probability. Okay, the second geometric measure we can use that we're looking at, the first one was that spinner that we looked at, and now we're going to look at one more. And that would be comparing sizes of things when we have more than a one-dimensional line, when I have a two-dimensional figure, like a dartboard. So we're looking at a simplified version of a dartboard, and if I ask you how many sections there are, you can all count them and tell me that there are 3 sections on there, okay, ignoring the little lengths giving you measures. We have 3 circles on there. So is it one, if I'm asking you what's the probability of throwing a dart and getting it in the bullseye center, is the probability 1/3? Because basic probability tells me you take the number of the event that you're trying to get, which there's only one, bullseye center, out of the total number of outcomes, and there are 3 different regions here. And if you're saying, I don't think so, that doesn't seem so likely, that's because you've become a good geometric thinker, and you understand that size of things varies, and you have to consider the size. So I don't think that darts would be a very competitive game or very much fun if it was 1/3 of a chance that you could hit the bullseye center. It just doesn't work out that way. What do we have to do? We have to compare the sizes of these. So we're going to draw on our knowledge of area to compare the sizes of 2-dimensional figures, and we're comparing areas. Remember, we're still calculating probability, which means we're making a fraction. The total in this case is going to be the big circle, so I'm going to consider the entire circle right here for my total. Okay, find the radius of that. We've got 4, which I'm going to use, but I also have to go into here. So my entire radius is actually 5. So area of the big circle is pi times radius squared, giving me 25 pi. And I'm trying to get in the little center part right here. Radius is 1 right there. So pi times 1 squared giving me 1 pi. Pi's do cancel in this case, giving me 1 out of 25 chance of hitting the bullseye center. Now I should stop for a quick second and just sort of preface this with, this is a situation where we are assuming that each spot on the board is equally likely of being hit. So if you have somebody that's really good at throwing darts and has really good aim, then the probability would probably not be 1 out of 25. Probability, we're considering random events. So this would be me throwing darts at the dartboard because I'm horrible at throwing darts, and believe me, if I even hit the board, I'm lucky. So if it hits somewhere on the board, it is equally as likely, no matter where I'm aiming, that it would hit in the center versus any other spot on that board. And how many spots do I have on the board that I could hit? You got it, an infinite number of spots. I can't count them. I have to calculate sizes to compare the areas and compare the regions to get the probability. Two more there. So you can pause the video and try calculating them. And actually the example at the bottom of your page is a little bit more with area. So you would be just fine to finish this on your own. I am going to go ahead and talk through these two, or at least B, and then if you want to pause it after that. B gets a little tricky just because you're trying to find, I like to say you're trying to find a shaded region. So I'm asking, what's the probability that the dart would land in this part right here? So that's not, that donut shape is not a circle, but we can find the area of that shape by doing a little bit of work with circles. So I'm going to take the easy part would be that the denominator is going to be the same thing. I'm still considering the whole board. What's the numerator? I'm finding that shaded region. So I'm thinking of it as it's my blue circle, but I just punched a hole in it. I just punched a hole in it and I took out this entire center, which is another circle. So I actually started with the 25 pi and I subtracted the center circle, which had a radius of, I know I scribbled it out, look on your paper. Radius is, yep, 3. So pi times 3 squared, I'm getting 9 pi for the area of that center circle that I'm punching out. Leaving me with the shaded region is actually 16 pi. That would be what I've shaded or highlighted there. So I've got 16 pi over my 25 pi. Pi's cancel, giving me 16 over 25. I can't reduce that. You can't take the square root of the top and bottom in a fraction. Everybody tries it. You gotta divide by the same number, so we're gonna leave it right there. And the last one there, in the inner ring, go ahead and try it. Okay, if you didn't finish C and maybe do A and B in number 6, and then pick up and check. You might be running out of class time depending on how quickly you got started with this. So if you want to do a quick check before you leave, I'm going to throw some answers up here and then I'll walk you through it. If you didn't get them, you can follow along, okay? Part C should have been 8 out of 25. And I'm going to show you 2 ways of getting that. Of course, the denominator should have been 25 pi still. Numerator changed. At this point, we've calculated the area of all of our circles. It's a visual thing. You have to recognize that what I'm talking about here, and of course I erased all my numbers, but that's okay. What I'm talking about here is I'm talking about the shaded region here, which was my, if you think back to a second ago, my green circle minus my red circle, which I'm subtracting away. Green circle, radius was 3, and I had 9 pi for that area. Red circle was 1 pi, because my radius was 1. So that gives me an answer of 9 pi minus 1 pi, 8 pi over 25 pi. Cancel the pi's, and I get the 8 out of 25. Other way you could have gotten that, if you think back to initial discussion with probability of all parts of an event happening has to add up to the total. So if you think about it, we just calculated the probability of being in this section or being in the center. Well, this inner ring is the only other option. Therefore, 1 plus 16 plus this has to add up to 25. Okay, so we could have gotten it by subtracting from 25 the 1 and the 16. Just another option. Last one on here, this is just to help you review a little bit with other areas. I really like this hexagon here. That's coming up on your final exam for sure, maybe on your quiz next week. Can you find the area of a hexagon? You would have needed to do that in here. Part A for this one, My simplified answer was pi over 8, which gives me approximately 0.393. You can also express probability as a decimal. So that one, I don't know if pi over 8 is a very nice fraction. I'll take either one, or I'll specify what I want your answer as. How did I get that one? I got that one by getting 36 pi for the area of the circle, and the area of the rectangle I calculated to be 288. That gave me my pi over 8, or 0.393. And the last one there, my final answer was about 0.174, and this one I am going to put as a decimal because it was a crazy calculation. Should have had 288 still for the denominator. And for the numerator, 288 minus shaded region. I have to subtract out both of the shapes in there, which is the circle and the hexagon. So the circle, 36 pi, is what I had calculated. But my hexagon, anybody remember how we find the area of a hexagon? If you did it correctly, you should have gotten 72 radical 3 for your area of your hexagon. I'm just going to give you a little hint here. Draw the triangle. The apothem in the center there is the length you know in that hexagon. Because this whole length is 12, that's going to be 6. So I think you can take it from there. If you need a little bit of help each other out. Do the area of the triangle multiplied by the number of triangles, or you did have a formula for that. Area of a regular polygon equals 1/2 the apothem times the perimeter. Okay, so help each other out if you need it. I know there's a lot of me talking, but that was the examples I needed you to see with geometric probability because we have several different cases.